So we talked about Green's theorem. What was Green? We had a couple different versions of Green's theorem, but the setup was we have a simple closed curve C bounding a region R, simply connected region R. And if I looked at the counterclockwise work or circulation, F dot dr, I have my field F, two-dimensional field with continuous first partials. This is the double integral over R of nx minus my dA. If I wanted the outward flux, then the outward flux was mx plus ny dA. So this was work, and that was flux. Okay, so that's kind of what we talked about yesterday. But the setup was we had a simply connected region. That means we had a region with no holes in it, and we had the counterclockwise orientation. So the question is, what if you've got holes in your region? All right. The first thing is, let's say we've got our region R, and the region R is going to be this. All right. And let's call the region R1 the whole thing. And then we'll call R2 and R3 the holes. First off, we have to think about what it means to define the boundary of something with holes as counterclockwise. So we talked about counterclockwise yesterday. If you're walking along the curve, if you're walking along the boundary, counterclockwise means that your left hand sticks to the inside of the region. So as I'm walking around this outermost boundary curve here, this is the direction I would walk. This is the direction I would walk if I wanted my left hand to stick inside the region. But if I'm on one of these interior boundaries, then for my left hand to stick inside the region, I actually have to go the other way. So that would be the counterclockwise orientation of these three boundary pieces. So let's call the whole boundary C. So let's call the whole boundary curve C. And C is made up of three parts. You've got the C1, the C2, and the C3. Right? Now, as stated, I can't use Green's theorem on this region because it's got holes in it. But I could use Green's theorem on these little regions down here, provided the first partials of m and n are continuous in the whole thing, right? In other words, we're not screwing up anywhere inside there. So what I could do is I could use Green's theorem So there's C1. That's got the same orientation as C1 up here. I could use Green's theorem on R1. If I want to use Green's theorem on R2 and R3, well, for R2 and R3, this is how the orientation would be to be counterclockwise. You notice that's the exact opposite of what the orientation is up here. So this wouldn't be the curve C2, but rather to be C2 with the opposite direction. And this wouldn't be C3, but it would be C3 with the opposite direction. But I could use Green's theorem on all these parts. So you see what's happening with the orientations here and how we're taking that region with holes in it and then turning it into three parts we can use Green's theorem on? Well, to use Green's theorem, I would need these to be counterclockwise though, with respect to R2 and R3. So that's what we're going to do here. So as pieces of the boundary for R, the part between the holes here, it goes this way. But for Green's theorem, for just R2 on its own, the inside of R2 and the inside of R3, we got to go the regular way. That's why they're opposite. So from R's point of view, this is the direction you walk. Oh yeah, I'm sorry. These are messed up. Hold on. Yeah, I did the exact wrong thing. I apologize. Yeah, you're right, Saran. Thank you. Yeah, you're exactly right. Thank you. There we go. Yep, you're right. Yeah, these here should be quote unquote clockwise. Yeah. All right. Now hopefully it makes sense. Yeah. So for yeah, exactly. So if I'm walking this way, the left hand is on the inside. And that's the opposite then of what they would be individually. Okay, thank you. Now are we good with the orientations? Welcome in, Zach. All right, so basically, if I look at, so the integral over C f dot dr, where C is these three parts. So up here, C is C1 plus C2 plus C3. I can write that as the integral over C1 f dot dr plus the integral around C2 f dot dr plus the integral around C3 f dot dr. All right, that's just the additivity of work. So I do work around the big one and then work around each of these two, add those up. So what I can do is I can rewrite that as the integral along C1 f dot dr, and then do the old minus a minus the integral around minus C2 f dot dr minus a minus integral around C3 f dot dr. So I'm just doing minus and a minus. And so this integral, I'll call this integral 1. Integral 1 is doing this thing here, and I can use Green's theorem on it. This is integral 2. Integral 2 would be finding the work this way, which I can use Green's theorem on. And then integral 3, once again, I can use Green's theorem on. Right? So what would Green's theorem say? I can convert now all of these to double integrals using Green's theorem. So this would be a double integral over R of the scalar curl, the nx minus my dA. So that would be an integral over what we're calling R1 minus a double integral over R2 nx minus my dA minus the double integral over R3 nx minus my dA. And now we can use properties of the double integral because I'm integrating the same thing. I'm looking at the double integral over R1, subtracting off the double integral over R2, as well as the integral over R3. And guess what? That means, right, I'm taking the integral over the whole thing minus the integral over the holes. guess what? That's just integrating over my original region R. Whoops. So what's the long and short of this? As long as you have, if you have a region with holes in it, and you've got the orientation compatible with counterclockwise. Once again, as you walk around your left hand, you always want to be looking inside, right? Reaching inside. Then you can extend Green's theorem. You can extend Green's theorem to something that has holes in it, as long as your partials are continuous inside the gaps. You follow? Inside the gaps. Now, another way I've seen this done, which is a little, you got to be a little careful with it. Another way you can kind of see why this would work is if you have like a complicated boundary like this. Once again, I'll try to do it correctly this time. So once again, imagine walking on these curves. You want to be, your left hand, you want inside the region. As you can imagine, doing this and adding in a path that goes out and back. So if you go out along a line segment and then back along the line segment, those two work integrals would do what to each other? If it's the same path, just opposite direction, they would. It'd cancel out. So another way you can think about this is if we start here and map it out this way, map out the region you're looking at. When you come in here, you go straight into this way, move around, and then back out, and then move around this way. I'm sorry, oops, I missed it. Move around, move over to here, move around, move back, move back, move back, and then out. It's almost as, and this is where we're going to put air quotes around this, it's almost as you're looking at the path traced out this way. That. In other words, you're sort of taking a little snippet out of here and here and basically getting rid of the holes. So it becomes one simply connected region. So that's a little homology 101 there. But however you go about it, I think this is the way we can understand it best at this level. Long and short of it is, as long as the orientation is consistent with the counterclockwise notion, we can use Green's theorem. All right, so where were we here? We were down here. Okay. So let's look at an example here. Let F be, this is our classic rotation field we've been playing with. R is the annulus. So what's an annulus? Well, you see you've got x squared plus y squared. Down here you've got it equal to 1. Down here you got it equal to 4. And we're looking at all the values between. So we know that x squared plus y squared equals 1. That's the what? Yeah. So we've got circle here, radius 1, and then another circle of radius 2. And since I want the pairs x squared plus y squared that are not only equal to 1 and 4, but between 1 and 4, then that's your annulus, right? Right. Now we want to orient R counterclockwise. So once again, I imagine as I'm walking along R, I need my left hand to be sticking inside the region. So on the outer circle here, the circle of radius 2, counterclockwise means as we would expect it to be. So if you imagine walking along here, your left hand would be sticking inside. But when I move into here and I walk along it this way, I'd have to turn around to get my left hand to be inside the region. So that would be the counterclockwise orientation on the inner curve. So it looks clockwise to us, but it's counterclockwise with respect to the region. So we all cool on why that is flipped in there. Just think of walking along. What direction would you walk along to do that? And so for 2, we can identify the m and the n. M for us is always the what component of the field. Yeah, the x component, so that would be 2y. And the n would be the y component, which is, and m and n have continuous first partials everywhere. Okay, so not only within the region R itself, but also within that smaller circle that's left out. So I can go ahead and hit this with Green's theorem. So the nx would be -1. The my would be 2. So Green's theorem says it would be the double integral over R of -1 minus 2 dA. So it's a double integral over R of -3 dA. And geometrically, that's just going to be what? What can I do with the -3? Yeah, take that out. That's -3 times the area. And we can get the area geometrically. It's just the area of the circle of radius 2. I just have to subtract off the area of a circle of radius 1. So that'd be -3. What's the area of the circle of radius 2? Yeah, pi times 2 squared, so 4 pi. There we go. And so our final answer is what? Now, what you could do is just go back to section 17.2, and you can do the integral along the outer circle, right? And then add the integral along the inner circle, going the other way, and show that that adds up to -9 pi. So you can check your answer on this one. It's not too bad. The parameterizations are pretty good on that. Find the outward flux of F across C. So once again, we can do that. Remember, flux is the double integral over R of mx plus ny dA. But in this particular case, my m is 2y and my n is -x. So the mx and the ny are both what? 0, which means this completely what? Zeroes out. Okay. So let's fire up GeoGebra and look at that. So once again, if you go into the course content, we got a couple of applets here. They put my spring courses in already. So vector calc, two-dimensional plotter. Let's put in our 2y and our minus x. There it is. And we can sketch in our, there's our unit circle, and then our circle of radius 2. Now remember, flux is trying to do what? Flux is looking for stuff that's going out of the region. You follow? But if you look at this field is just doing what? Yeah, it's just rotating. It's just going along. So there's not going to be any flux. So it's not that there's a net flux of 0. It's not that there's as much, coming out as going in, right? It's not that there's as much going out this way that's going out this way, and then the net flux is 0. It's 0 all the time. The divergence of that field is 0. And once again, we talked about divergence last time. When we come back from Thanksgiving break on Monday, we'll talk about divergence and curl in more generality. But that's what's going on there. Okay. All right, stream functions or flux potential. So stream functions is the actual name. I call them flux potentials because stream functions do for flux calculations what potentials do for work calculations. So let's recall here when we had our fundamental theorem of line integrals on Monday. This was our work or circulation. If we had a function where m is phi x and n is phi y, then this integral phi x dx plus phi y dy is just integrating d phi, and you get the change in phi. Okay? Phi was called the potential function. And then we could measure the work or circulation by looking at the change in potential. That's your fundamental theorem of line integrals. All right? Well, let's look at flux. So flux, instead of working along the dr, we're looking at the normal direction, dn. And that has m dy minus n dx. Okay, so that goes back to the r of t. Okay, so what we want is we want to come up with a function. We're going to call it psi. So we'll call it psi. And here's what we want. We want this to work out to be the change in psi. All right, so for that to happen, what do we have to do? Well, let's rewrite this. We'll put the x part first. Minus n dx plus m dy. So this would have to be psi x. So psi x would be minus n, and that would have to be psi y, would have to be m. And if I could figure that out, then I could get my flux by integrating psi x dx plus psi y dy, which is integrating d psi. That gives me the change in psi. So that would be that. So this would be called, psi is called the stream function. And we'll talk about why it's called the stream function here geometrically in a minute. But what would have to be true? What would be the condition? So when we were looking for these potentials back in the day, we used Fubini's theorem to try to figure out when this would happen. So if I took my, that'd be phi xy, and then that would have to be phi yx, which would be nx, and that's where we came up with our exactness condition. My equals nx. Or, if I think of it in terms of curl, nx minus my is 0. So we mentioned that yesterday. We'll talk more about that next week. So what would be true over here? So if phi x is minus n, so if phi x is minus n, then phi xy would be minus ny. And if phi y is m, what would phi yx be? mx. So for this to be true, I would need mx to be minus ny, or mx plus ny to be 0. And once again, this means that the divergence is 0. So, okay, our power just went out again. So I'm going to finish the lecture here, and then I'll upload the video. So I apologize for that. All right. So basically what we're saying here is this. So for the work, if the nx minus my is 0, we can get the work done by looking at the difference in the potential. For flux, if the mx plus the ny equals 0, we can get the flux by looking at the change in psi. Okay? So remember, if mx plus ny is 0, we say that the field is source free. So if I look at our function here, our rotation function m, so if I look at our function here, I think I'm still recording. So our m here is 2y, our n is minus x, and sure enough, as we saw, mx and ny were both 0. So mx plus ny is equal to 0. That means that there's a stream function. So for my stream function, phi x is, well, let's look. Phi x is minus n, which is x. And then phi y would be 2y. And you put these together and you would get phi equals 1/2 x squared plus y squared plus a constant. Okay? So if we want to find the flux of F across the quarter of the unit circle, which lies in the first octant, or first quadrant counterclockwise, so if we're going this way, and we want the flux of this field, then I can look at the change in the stream function going from 1, 0 to 0, 1. So that would be psi at 0, 1 minus psi at 1, 0. And if you go through and plug that in, psi at 0, 1 is 1. Minus psi at 1, 0 is 1/2. And that gives you a flux of 1/2. Okay? All right. Now, why are these things called stream functions? Well, there's a couple things at play here. Remember, if you have a scalar function psi, the gradient of psi is orthogonal to the level curve. Right? But if I look at the gradient of psi, I'm getting the minus n comma m, which is orthogonal to the field f. So that means that the level curve of psi is going to be parallel to the field because both of these things are orthogonal to the gradient. And you can kind of see that here. So here's the field that we were looking at. It's a rotation field. And I've graphed here the level curves of psi. And so the level curves of psi follow the field. So that's why they're called the streamlines or the stream function, or lines of force. You might see them contacted that way. All right, the last thing to talk about here is harmonic functions. This would be a nice topic for a project to kind of dive deeper on this, harmonic functions. So if you've got a conservative field with potential phi, then phi x is m and phi x is y. If in addition f has a flux potential psi, then m is also psi y and n is also minus psi x. So if we go to look at phi xx plus phi yy, looking at the second partials here, well, that'd be phi xx plus phi yy. So that would be your mx plus ny, which as we've seen is going to be 0 because that would be phi yx minus phi xy equals 0. This shows that the potential function here, phi, satisfies the Laplace differential equation, and therefore it's called a harmonic function. And once again, you can go and look and see what the Laplace equation models. I think it's vibrations on a drumhead or something. So as an example, show that this function here, phi e to the minus x sine y, is harmonic. Find the corresponding gradient field and show that it's conservative and source free. So basically all we do here is we look at the phi x, and then the phi xx, the phi y, and the phi yy. And you can see right away that phi xx plus phi yy completely cancels out. So this shows that phi is harmonic. So now we look at the corresponding gradient field. So to get the gradient field f, that's just phi x comma phi y. So the field f they're talking about is the gradient field. So that's going to be minus e to the minus x sine of y and e to the minus x cosine y. So there's that. And so I can call this my m and I can call this my n. And I would just need to show that my equals nx. That shows that it's irrotational. That shows that the nx minus my is 0. And then just show mx plus ny is 0. That'll show that it's divergence free. And we've actually got, well, for my equals nx, you can see here the my would be minus e to the minus x cosine y. And that would be the same as nx. And then for the mx plus ny equals 0, that's exactly this calculation here. Okay? All right, so unfortunately we lost power there in the middle. I'm going to get this uploaded as nice as possible. Have a good Thanksgiving break, folks, and I'll be checking email once or twice a day over the weekend if you've got any questions. Take care.